Finding the value of a limit through a graph is definitely time consuming, so we want to be able to do it by an algebraic means. So we'll take a look at first evaluating definite limits, which means we have our variable x approaching a certain value, and then later we'll talk about and look at, well, what if it's approaching infinity? So for the most part, and like I alluded to in the graphing section, is sometimes all we have to do is plug in the value of x. And now I need to be cautious here in that x never actually gets to that number. That's the whole idea of the limit. It gets close to the number, in fact, infinitely close to the number, but never actually gets there. And the whole idea of the limit is that if x is getting close to that number, then what's y getting close to? What's its limit? So as I take a look at this first example, let's see, can we just put 4 into this? So I would get 4 squared plus 3 times 4, so that's 16 plus 12, and I get 28. So that would be the limit, meaning as x approaches 4, the limit that y gets to is 28. No, it doesn't actually get there, it gets close to there. Let's take a look at this example over here on the right. What if x approaches -2? Now, it may not be clear here, but that is a 3 right there. So I would do 4, put in a -2 right here to the third, plus 1, all over -2 minus 5. Now, we want to be careful. You need to know the order of operations. Exponent first. Do not do 4 times -2. Exponent first. So that's going to be -2 cubed -8. So I have 4 times -8 plus 1 all over -7. So that's going to be -32 plus 1 is -31 all over -7. So 31 over 7 is our limit. And each of these actually works out easy like that. I just put in this number, 4 in this case, into each instance of x, and that will give me my limit. But it's not going to be that easy for all questions. We'll see that here in a minute. So this limit is -5. And this last example, and this is about as simple as evaluating a definite limit could get, is you just plugging in the number. So absolute value here. So I have absolute value of -1. You do the absolute value last. So now absolute value of -1 is 1. So 1/6. So our limit here is 1/6. All right. Let's take a look at some tricky ones. And we'll go over this term here, removable discontinuity. So when we took a look at the graphs, we saw that, if we had like a jump in our graph, that this would be called a discontinuity, or it was discontinuous. So what we are thinking about when we have a removable discontinuity is perhaps there's like a hole right here. And the whole idea of a removable discontinuity is, could I just fill that in and make it continuous? So let's take a look here. On this example, if I put 3 in and directly 3, I would get a 0 in the denominator because 3 minus 3 is 0. And we can't divide by 0. That would be lead us to an infinite situation, possibly an infinite situation. So let's see if there's something we can do. A big hint here is we have this quadratic, and we could factor that. So let's factor it, just see what we get here. And of course, Mr. Kane set this up so it doesn't work. So I'm going to actually say that this one, you cannot remove the discontinuity. So let me change the problem a little bit so that we can remove discontinuity. So I'll delete all this stuff out of the way. And let's take a look. What if it had said the limit as x approaches 3, and then I had still that x minus 3 down here, but perhaps instead I had x squared. Let's have a minus over here. Let's have a minus 3. And let's have a plus. Let's have a minus 2x. I think that'll do it for us. So if we factor this, I think we'll find a removable discontinuity. So we factor it, and now we see that we can actually cancel the x minus 3. See, I removed it, whereas up here, I was not able to remove it. It was not removable. So now that I've removed that, if I put in 3, I have 3 plus 1, which is 4, and that's my limit. Let's take a look at this example, and maybe we have a removable discontinuity on this one, and maybe we don't. Let's see. So if I put in -4, let's just even take a look. Do I even need to remove the discontinuity? Is there even one? Let's see. If I put in -4, and I'm just looking at the denominator, that'd be 16 minus 12 minus 4, and yeah, I get a 0 right there, which means I'm going to have to try to cancel something in order to evaluate this limit. So I'm going to do the limit as x approaches -4, and I'll factor that in numerator, and I'll factor the denominator. Okay, and I didn't factor the numerator correct. One of those should be plus. Cancel. All right, so I removed the discontinuity, hopefully. So now I have the limit as x approaches -4 of x minus 4 over x minus 1. So that's going to be -4 minus 4, -4 minus 1, so -8 over -5. So that's 8 over 5. All right. Oh, that's pretty simple, but what about this? Now I have a 9, and if I put in the 9 right here, I do get a 0 in the denominator, but I'm not going to be able to factor anything. But this root gives us a clue. Now, if I had a root, and I'll work down here at the bottom, what if I had 3 over root 2? Well, a little trick we said is we can't have a radical in the denominator, so we would do this rationalization. And we get 3 root 2 all over 2, and we'd say that's rationalized. And likewise, if we had 3 over, say, 2 plus root 5, now we couldn't just multiply by root 5, we'd had to multiply by the conjugate. And when we multiplied by the conjugate, we were able to rationalize and get our denominator to be not have a radical. So, and I'm not going to finish simplifying that. You already know that stuff. So what about here? Now, I don't have a radical right here. But what I want is a trick in order to get this denominator so that if I put in a 9, I don't get a 0. So I don't have a radical in the denominator, but I do in the numerator. What if I just rationalized the numerator and basically moved that radical down to the denominator? So in the numerator, I would have x minus 9. Oh, that's interesting. And then in the denominator, well, I'm not even going to bother multiplying that out. And why not? Well, because I see that I can cancel my x minus 9. Now, what do I get on top when I cancel that x minus 9? Well, a 1. I don't get a 0. I get a 1. So I have 1 over root x plus 3. And I'm trying to take this limit. So technically, I should be writing limit each time. I was being lazy bum. So now if I put in the 9, I'm going to get equals 1 over root 9 plus 3. So that's going to be 1/6 because root 9 is 3 and 3 plus 3 is 6. So 1/6. And I'm going to do the same thing here on the one on the right. I'm going to rationalize. Because if I put in 25 right here, square root of 25 is 5, and 5 minus 5 is 0. And I'm not necessarily going to bother multiplying everything out because my hope is that something is going to cancel. So at the top, I have x plus 25, root x plus 5. And at the bottom, I'll have x. See, now when I multiply this out, it's that times that, that times that. So I'm actually literally getting root x squared plus 5 root x. And then when I do this one, minus 5 root x minus 25. So this thing in the middle is going away. All right, so right here, we're going to have minus 25 if I finish multiplying that out. Why did I write a plus right here? That should be a minus. It was a minus, trust me. So the x minus 25's cancel. And I'm doing the limit as x approaches 25, which is going to equal the square root of 25 plus 5, which is 5 plus 5, which is 10. So if we were to graph this, and if we were to graph that, we would see that if we go either from the left or right, no matter what, we are going to approach each of these numbers respectively.